Alright, today I got this DC motor. It came out of a Treadmill. A little bit of background before I took it out of the Treadmill. This isn't from my Treadmill, it's a friend of mine's. They've been using it, and they had said, a couple of times they had to like help the treadmill get started. They had to start pushing the belt, and then eventually the motor would start to pick up, and even then they said it sounded kind of clunky. Did a little bit of diagnostic work on the machine, disconnected the motor leads and tried to apply power or voltage directly to the motor. Couldn't get it to spin, so we thought that was the most likely thing that was wrong with it, and sure enough I've done a couple other simple things and determined it is the motor that's not working properly. So I think we can buy a replacement motor. Replacement motor is like $100. It's not terrible, but there might be something simple about this motor that's not working, and rather than chalk it up to just a bad motor, we're going to try to take this thing apart or do a little bit of diagnostic work and try to figure out what's wrong. I also have a smaller DC brush motor just as an example of what a good working motor should look like, and maybe a couple of tests you can do, try to figure out what might be wrong. So the first thing is to really identify what we're expecting of this thing, so that way you can try to figure out what it is that this is supposed to be producing in order to get that. So we're obviously expecting this motor to spin and put out some torque. You can see this is from a Treadmill. It's got its horsepower and voltage ratings on here, and right now I just have a simple 18-volt handheld tool battery. And if we were to apply some voltage to this, it should in fact spin. Let me get some wires. So if we apply voltage to this guy, nothing. Now take the other little baby brother over here. If we flip the polarity, we should get the motor to go in the opposite direction. So that's one nice thing about DC motors. They're pretty simple. All the commutation is handled inside of the device. So if you give it a DC voltage, it's going to spin one way. If you reverse that polarity, it's going to spin the other way. And they're also really easy to do speed control, because you can do a couple different schemes. Pulse width modulation is likely the one that's on the Treadmill, where you give it kind of a square wave of voltages, and it's effectively averages the voltage when the voltage is on and voltage is off, the duty cycle, so to speak. If it's 50%, you'll effectively be applying half of that voltage, and you'll go half the speed. So like we said, we're expecting this thing to output some torque, and it has to, in order for it to spin, it has to generate enough torque to overcome any amount of resisting torque that there is. When it's just at the motor level, it's pretty much just going to be the bearings, and then perhaps some friction at the brushes. The brushes and the commutators, how you get the DC voltage onto the electromagnetic part of the rotor. So there's definitely going to be some friction there. But if we can just spin this thing by hand, it's unlikely to be any kind of appreciable friction that's resisting this motion. And the real application would be the load of the person on the treadmill. It's obviously trying to move that load. That's the point of the motor in the first place. So if we say, okay, it's unlikely to be too much resisting torque, we can spin it freely by hand. It's likely that this motor isn't generating enough torque, or effectively any torque. And in order for this motor to generate torque, you need to have two magnetic fields. One of them is provided by the stator, and this is going to be permanent magnets. So those are going to be permanent magnets that are fixed to the side of this case, the inside of this case. So those will have a permanent magnetic field, and then you need to generate a magnetic field on the rotor such that you get some torque. So you need those two magnetic fields, one on the stator, one on the rotor. You need the orientation of those fields to be correct to produce appreciable torque. So that's effectively what the commutator is supposed to be doing. It's supposed to be generating the magnetic field on the rotor with the proper orientation so that you get some torque. And then you also need it to be in close proximity. So you couldn't have this stator be 1 foot diameter. You know, we're likely going to see a pretty small air gap between the rotor and the stator. So if you think about all those things, you know, it's pretty, this motor was working at some point. You know, the treadmill worked for a couple of years. It's hard to change permanent magnetic field unless the magnets are just destroyed or, you know, severely been damaged in there. Same thing for commutation, unless the commutator rings, you know, have become loose or, again, you know, pretty grossly damaged. The orientation of the magnetic field generated should be pretty much the same. That, again, hard to change. Same thing with proximity, you know, unless you've grossly damaged some parts, the air gap shouldn't have changed. So it's likely that we're just not generating a sufficient magnetic field on the rotor. And to do that, to generate a magnetic field on the rotor, you're effectively got a solenoid, you know, many solenoids, however many number of poles there are. So you got some windings around an iron core. You need a certain number of windings. You need the material that the rotor is made out of to be some sufficient material properties. It's likely a lamination stack, so it's some kind of magnetic core material. And then you need to put enough current through the rotor windings. So assuming you've got the right material in the core, you've got the right number of winds, and you put enough current through it, you should be able to generate a magnetic field that, in conjunction with the permanent magnetic field, should produce enough torque to get this thing to spin. So similarly, you know, the number of windings is difficult to change, or it'd be hard to have that change from its original condition. And the material properties of the core, unless they're badly delaminated or grossly damaged, that would be difficult to change as well. So I'm thinking the most likely is that we're just not putting enough current through here. And to get current, in this case at least, when the motor's not even spinning, we can effectively neglect most of the inductive and other back EMF things that might affect your current when the motor is actually spinning and trying to move a load. When it's just static, the amount of current going through these windings, assuming you get to steady state, is just your simple V equals IR, or I equals V over R. So it's either that where voltage isn't high enough, but, you know, voltage is too low, or our resistance is too high. So going into this, I had already done a simple check on the resistance, but I'll show you that here. Is that if we measure the resistance, this will be through the brushes, right? So through our leads, each one of these wires is going to a brush. Those brushes should be making contact, or good contact, with the commutator. And then depending on how many portions of the commutator it's touching, it will go through one or more rotor windings, and we should be able to measure its resistance. If you can see here, that's the mega ohms, so we're measuring incredibly high resistance. Sometimes it's going open load. So clearly this is showing much higher resistance, and applying virtually any voltage is going to get us effectively zero current. I'm rotating the rotor here just to show it as we go around. It's very high resistance virtually everywhere. Now we can do the same thing on our little motor over here. We're still hooked up to the leads, and what we should see is a pretty low resistance, because we know this motor is in pretty good condition. And we do. We see 16 ohms. As we rotate around, it's obviously, you know, contacting, perhaps it's contacting a couple different commutator rings, or it's we're picking up some resistance as we rotate. It's making it bounce around a little bit. But nonetheless, we generally have low resistance, which is why that motor is able to spin. So we know that when we apply voltage, the current path in this motor has to go through this wire, through some number of connections to get to the brush. There's likely a spring in there to preload the brushes onto the commutator. Then there's a interface between the brush and the commutator, and then you know, somehow that commutator ring or commutator slot has to interface with the rotor windings, and then there's all of the wire, you know, the windings themselves. Those have to go back onto the commutator, back through the other brush back through the other wire, and back to your voltage source. So right now we don't know exactly where that open might be. So the first thing we can do is start taking out these brushes, and we can measure resistance from the connection that would be connected to the controller board of the treadmill and all the way to the brush. There's not an easy way that we can measure the resistance of the brush to commutator interface, at least not in this configuration, but we can try to make some assessment of whether or not there's an actual break in some of this wiring leading up to the brush, and then we can maybe take a look at the commutator, see if it's dirty, or take a look at the brushes, see if those are dirty. So let's try to get these out. Okay. Okay, so that brush doesn't feel like there's anything preventing it from going in all the way. I was suspecting it's touching the commutator there. Let's see if I can tilt this up. So we can see the commutator ring in there. And this looks like that brush could easily make contact with the commutator ring. Whether or not there's actual appreciable resistance to the interface, we'll see. So we know we should be able to take a resistance measurement from this connection to this brush and see a low resistance. If we simply take a resistance from there, move this back in view here. So we're measuring from the connection that would connect to the treadmill controller board to the brush. We're getting 1.5 ohms, so very low resistance through this path as expected. That would be, that should be kind of visually obvious if there was any kind of break in the wire, a break at one of these interfaces. Let's get the other brush out and do the same thing. And then we can take the motor apart and take a look at the commutator ring and the windings. Okay, so same deal. Okay, about the same, 1.5 ohms. Okay, so both brushes, both the wires, and all the fittings and all these connections, the crimped connections and everything, are still in good shape. So we've pretty significantly limited the area where there can be any kind of appreciable open or really high resistance to inside of the motor, and specifically to the commutator bar and or the windings themselves. So let's try to crack this thing open, get the rotor out. I'm sure I assume at the assembly they have a nice fixture to do kind of rotor installation. We're just going to have to wing it and try to pull it out of there safely if we can. So there's a fitting on this end. This is likely a piece of threaded rod that goes through this entire case and clamps the whole thing together. So it's likely preloading this bearing, and there should be a bearing on this side as well. So we'll have to make sure we don't lose any parts in this process here. So this is our commutator. So it's not going to spin nicely anymore because this bearing is no longer supported by this case. So this counterbore here is where this bearing would sit, and this case to the motor aligns itself to the inside diameter of the stator to capture and hold that bearing, so to keep the rotor centered inside of the stator. Tip it up there. So you can see there's our permanent magnets. These big, I'll try to support that while I show. These are the permanent magnets inside the stator. This is obviously our rotor with the commutator bar. So I'm going to try to get that rotor out, take a better look at it. In fact, while it's in there, let's do a quick resistance measurement if we can. So we know that if we took this apart, kind of like this, I think our brushes were, approximately in this orientation. So if we try to take a resistance measurement from one of these commutator bars to one on the opposite side, that should be, the same two portions of the commutator that we were attempting to measure when we were doing our resistance measurement of the entire circuit before. So if those are still showing high resistance, it's likely that the interface between the brushes and the commutator was okay, and that's something contained with the rotor. If these are reading okay, then maybe it is just that we have to clean up the commutator and maybe clean up the brushes and put the thing back together. So let's see here. So I'm going to say approximately here, maybe one of those. Okay, so we're still reading well into the mega ohms. Well into the mega ohms for any commutator ring that's close to the opposite side. Okay, so it seems that we can't rule out the interface because that was we can't completely rule out the interface between the brushes and the commutator because that wasn't something that we've directly measured, but we can say even if that was good, we're still going to have some issues because this rotor is showing considerably higher than it should. I'm expecting something in the neighborhood of 5 to 10 ohms, not even hundreds of ohms, let alone kilo ohms or mega ohms. So let's take this thing out if we can. See how gracefully we can do this here. Not so gracefully. There we go. So we got a little spring. We'll have to make sure we get that back in there so that this bearing gets preloaded. Okay. So that is your rotor. So we know we need to be low resistance through this commutator bar, which should be, it looks like it's copper. Yeah, we get, effectively no resistance, less than an ohm. So the brush is clearly making contact in this, section that is worn away. Those brushes are, some kind of graphite or carbon. So, here in the area where we'd be making contact with the brushes, down to still the portion of the commutator that's solid material, we're very, very, very low resistance. Piece of copper exposed on that winding. Okay, so that's really low resistance. So we know for that winding specifically, we have a low resistance, material itself, which is expected, but then we also have a good connection between this commutator ring and the actual wire itself, the wire of the winding. So I'd like to check 180 degrees, if I can, find a bit of exposed bare copper wire to confirm if it is in fact in just one of these windings, or if there's a bad joint on some or quite a few of these commutator joints. So looking at these windings a little bit closer, what I originally thought was that this was one solid wire that was wrapped through this interface here. What it turns out, it appears that I think all of these, or at least a majority of them, are two separate wires that it looks like this piece of copper here is initially pointed down, and then they put these two wires in of the windings and then bend them up, kind of crimping the windings in there. And what I noticed was that this guy was loose. And the other thing I noticed, so previously I was only doing resistance measurements from one of these wires up to here and saying that that was good. That we got 1.8, 1.5, sometimes below an ohm. And if you do this one that was loose, there we go. So there's barely any pressure. I'm getting 10 mega ohms, 9. Put a little bit of pressure on it, 1 ohm. So I'm going to do a check of all these and see if there's any of these others that are in a similar boat. It's possible that that is the one winding that wasn't making a good connection and screwing up the rest of the motor. So I've gone through and measured resistance to all these crimped connections, or what appears to be intended to be a crimped connection. I've numbered all the bad connections, so every single one of them I drew a little green dot next to them. They all are on the right hand side, so it appears to be something about that crimp connection, or the way they had to bend the wire in to get it into that crimp connection, that is causing those to fail, or be more likely to fail. There was a total of 10, so that's quite a few bad connections. It's surprising that this thing worked as long as it did and as well as it did for that time. Oh, it's a good example here. You can see some of these winding wires have just broken. I'm not sure if I'm going to be able to solder them, or how long I would expect that solder joint to last. This is copper, so it's an incredible heat sink. I may not be able to get it hot enough to flow solder into those. So we're going to see. Okay, so we're able to actually make reasonable solder connections to all those broken joints. And I'm pretty sure, looking pretty closely, none of them have accidentally been shorted to the adjacent commutator bar. So I'm thinking if we now take our multimeter and go to opposite commutator bars, we're now going to see much lower resistance, something more along the lines of what we expected. So this is approximately, there we go, 0.8 ohms. Let's try this one, 0.9 ohms. There we go. I'm thinking this thing is going to spin when we put it back together. Okay, so we got this thing back together. I'm going to do the same test I did right in the beginning when we did the resistance measurement. Let's get that away. Resistance measurement from positive to negative lead. So now we should be measuring back through this wire, through a brush, onto the commutator ring, through some number of windings, back out through the other commutator ring, the other brush, back up this other wire. And you can see now we are measuring very, very low resistance. Probably an intermittent connection here with my leads, and as I spin around, finds itself at about an ohm, ohm and a half, 2 ohms. So I did try to clean off the commutator as well, sand that up a little bit, make sure I didn't have any shorts, after my solder job there. Alright, now let's try the battery. Hopefully. There it goes. Okay, if we switch polarity, we should go the other direction. There we go. So, a couple of botched crimp connections. And that's all that killed this guy. So you're talking about a probably over $1,000 treadmill, $1,200 treadmill. The thing runs Linux and, you know, has web connection and, you know, touchscreen and everything on it, and, you know, dead after only a couple of years because of a few bad connections on a motor. So again, just knowing what we're expecting out of this thing, you know, the physics behind what makes a motor bad or what makes a motor not spin. Able to do a couple of simple quick tests and take the thing apart, see what's wrong, get it going again. Alright, thanks for watching.